Hi everybody. In this video I'm going through a bunch of linear algebra exam 2 review problems and solutions, though many of these problems could show up on your exam 1. These problems involve linear transformations in matrices, determinants, inverse matrices, doing matrix multiplication, a little bit about spanning and linear independence, difference equations, equations of planes, and the basics of vector spaces and linear transformations in the abstract setting. So you can see in the very first problem here that we are starting with a 2 by 2 matrix, and we're trying to use a shortcut formula that my students should know, and really everybody should know, in the 2 by 2 case involving the determinant of A to find the inverse matrix of A, and evidently we're assuming the inverse matrix will exist, and you can double check that that is true. The determinant is non-zero. It's 1 times 8, which is 8, minus 2 times 3. 8 minus 6 is 2. That's non-zero. That's enough to say that this matrix is invertible. Circle your final answer, and then in part B, use your answer from part A to solve this equation right here, ax equals b, where b is this fixed vector and x is an unknown vector. We'll need to multiply by A inverse. So let's go ahead and first use the shortcut formula. In general, it says that if A equals the matrix whose entries are little a, little b, little c, and little d like this, that the inverse matrix, when it exists, is 1 over the determinant of that, which is 1 over AD minus BC, times a 2 by 2 matrix where you swap the entries on the main diagonal, the A and the D, like this, and you negate the entries on the off diagonal. Put negative signs in front of them. Of course, if B and C were negative to begin with, then they would become positive when we negate them. So let's go ahead and apply that here. A is 1, B is 2, C is 3, and D is 8. Therefore, for this matrix, its inverse matrix is this. 1 over the determinant is 1 over 8 minus 6 is 1/2. I swap the 1 and the 8 around like this to get an 8 up here and a 1 down there, and negate the off-diagonal entries like this. 1 over 8 minus 6 is 1/2. I can distribute the 1/2 through the matrix, multiply it by each entry. 8 times 1/2 is 4. Negative 2 times 1/2 is negative 1. Negative 3 times 1/2 is negative 3/2, and 1 times 1/2 is positive 1/2. We may want to take the time to just quickly check that it really worked. If I multiply A inverse times A in that order or the other order, I should get the 2 by 2 identity matrix. Let's see if that happens, just as a check to make sure we didn't make a mistake. It's not required in the problem. There's A inverse. Here's A. Multiply the entry for the upper left corner of the product will be the dot product of the first row of the matrix on the left with the first column of the matrix on the right. 4 times 1 is 4, plus negative 1 times 3 is plus negative 3. 4 plus negative 3 is positive 1. Then for the upper right entry, it's the dot product of the first row with the second column. 4 times 2 is 8, plus negative 1 times 8 is 8 minus 8 is 0. Negative for the lower left entry, it's negative 3/2 times 1 plus 1/2 times 3/2. That's negative 3/2 plus 3/2 is 0. And finally, for the lower right corner, I do the second row with the second column. Negative 3/2 times 2 is negative 3. 1/2 times 8 is 4. Negative 3 plus 4 is indeed 1. Okay, looks like we've done it right. Now, let's do part B. To solve this equation for the unknown vector x, we need to multiply both sides by A inverse. Or you can just write down the answer. It's ultimately going to be A inverse times B. This simplifies to A inverse A times x. And A inverse A is the 2 by 2 identity matrix, I times x, so this becomes x. And that's enough to say that x will equal A inverse times B. So here's A inverse, 4, negative 1, negative 3/2, and 1/2. Times b. This b vector is given to be negative 5 for the first component and 2 for the second. This is going to be a two-dimensional vector. Do the dot product thing again. The first entry is going to be 4 times negative 5 is negative 20, plus negative 1 times 2 is minus 2. And the second entry is going to be negative 3/2 times negative 5 is positive 15/2, plus 1/2 times 2 is plus 1. And that's going to give us negative 22. 1 is 2 over 2, so this looks like 17/2. Negative 22, and then this would be 8.5. Looks like it's the answer. If we want to double check it, we can do a multiplication. We could take A, the original matrix A, 1, 2, 3, 8, and multiply times this vector, negative 22 17/2, and we should get the b vector when we simplify. 1 times negative 22 is negative 22. 2 times 17/2 is plus 17. 3 times negative 22 is negative 66, and then 8 times 17/2 will be 4 times 17 will be 68. Yes, this does simplify to negative 5, 2. Okay? So that is our solution. On to the next problem. We're letting A be this 3 by 3 matrix, and I'm telling my students to show the details of row operations, details, on a certain augmented matrix to find A inverse, and then circle your final answer. This is called the row reduction algorithm to find A inverse when A inverse does exist. Evidently it will here, which is typical when the entries in your matrix are random. What I'm doing here is I'm creating now a 3 by 6 matrix whose 3 by 3 part to the left of this dashed line is A, and whose 3 by 3 part or block to the right of this dashed line is the 3 by 3 identity matrix. And this is the matrix I want to do row operations to get to reduced row echelon form. If this part of the matrix, this block, becomes the 3 by 3 identity matrix, then whatever's over here will be A inverse. Okay, so I'll do these as quick as I can. I want to get zeros below the leading one in the first row, so I need to multiply row 1 by 3 and add it to row 2. So I'll keep row 1 the same here initially. If I multiply this by 3, I get 3. Add to negative 3 gives me 0 as I want. That's why I multiplied row 1 by 3 to add to row 2. 0 times 3 is 0, plus 1 is 1. Negative 2 times 3 is negative 6, plus 4 is negative 2. I have to keep going. I have to do it over here as well. 1 times 3 is 3, plus 0 is 3. 0 times 3 is 0, plus 1 is 1. And 0 times 3 is 0, plus 0 is 0. Also, I'm going to do another row operation. I'm going to multiply row 1 by negative 2 and add it to row 3 so that I get a 0 right there. 1 times negative 2 is negative 2, plus 2 is 0. 0 times negative 2 plus negative 3 is negative 3. Negative 2 times negative 2 is positive 4. Add 4, and that gives me positive 8. Keep going. 1 times negative 2 is negative 2, plus 0 is negative 2. This still gives me a 0, and 0 times negative 2 is 0, plus 1 is still a 1. All right, that's the first couple steps shown on one line there. Now I've got a leading one in the second row. I've got a pivot position there, that's called. I've got a pivot position here and a pivot position there where I have leading ones. I want to get a 0 below that, so now I'm going to multiply row 2 by positive 3 and add it to row 3 to make that become a 0. Keep the first 2 rows as they are. Those don't change. And now I will get 0, 0, and then I need to figure out the other ones. So again, I'm multiplying row 2 by 3, adding it to row 3. Negative 2 times 3 is negative 6, plus 8 is positive 2. 3 times 3 is 9, plus negative 2 is 7. 1 times 3 is 3, plus 0 is 3. And then 0 times 3 is 0, plus 1 is a 1 still. Now I want to get a leading one in this pivot position in row 3. Keep the top 2 rows the same. I need to multiply this by 1/2 to get a 1 there. I need to multiply everything in that row by 1/2, so I am going to get some fractions. That's okay. Finally, I want to get zeros above all leading ones. There's already a 0 above this one. I need to get zeros here and here. And that shows me it will be invertible. I will be able to make the left-hand block into the 3 by 3 identity matrix. I keep the bottom row as is. That will be the last row of my inverse matrix. I'm going to now multiply row 3 by 2 and add it to row 2 to get a 0 there. And also row 3 by 2, add it to row 1 to get a 0 there. Let's do it for row 2 first. 1 times 2 is 2, plus negative 2 is 0. 7/2 times 2 is 7, plus 3 is 10. 3 halves times 2 is 3, plus 1 is 4. Hoping I'm not making a mistake. 1 half times 2 is 1, plus 0 is 1. And now do it for the top row. Again, multiply row 3 by 2, add it to row 1 now. 7 halves times 2 is 7, plus 1 is 8. 3 halves times 2 is 3, plus 0 is 3. And 1 half times 2 is 1, plus 0 is 1. And this, if I have not made any mistakes, should be the inverse matrix. Let me just quickly double check that I did this on Mathematica ahead of time. Let's see if I can find that here. Let's see, yeah, there we go. Did I get the right answer? Right there, 8, 3, 1 across the top row, 10, 4, 1, and then 7 halves, 3 halves, 1 half. Yes, I got the right answer. Okay, wanted to double check that. You could also double check it by multiplying by A and seeing that you get the 3 by 3 identity matrix. All right, we will make use of technology, including a calculator, at various points here, including doing RREF to reduce row echelon form on a calculator. On to the second page. Here I got a 3 by 3 matrix, and I'm saying use any method you want to find the determinant of this by hand with calculator to help show your work, okay? Part B, what about the determinant implies A is invertible? Evidently, it must be non-zero. That's what's going to imply it's invertible. Part C, find the determinant of the inverse without actually finding the inverse matrix. We don't want to find an inverse matrix. Okay, usually for the determinant, there's something called the cofactor expansion across any row or any column. And if you got zeros in a particular row, like if you had 2 zeros in the first row, you'd want to do it across the first row, for example. This matrix doesn't have any zeros in it, so it really doesn't matter what you do the cofactor expansion across. As a default, let's go ahead and do it across the first row. That'll be the way I compute the determinant. I will remind you that you can also calculate the determinant with row operations, though I won't show the details. So, cofactor expansion across the first row, that means take the first entry in the first row, -1 in this case, multiply it times the determinant of the 2 by 2 submatrix that I get by deleting the row and the column of that first number, the first row and the first column. If I delete the first row and the first column, I get that 2 by 2 submatrix. Its determinant gets multiplied by the -1. Let's write it symbolically like that. If this -1 had been a +5, I'd put a +5 there. But it was a -1, so I'm putting a -1 here. Then you put a minus sign. Whether the second entry in the first row is positive or negative, put a minus sign. It's very easy to make mistakes here. Put a minus sign, then put that second entry in the first row. 2 minuses, of course, will make a plus. That gets multiplied by the determinant of the 2 by 2 submatrix that I get when I delete the first row and second column, where that second entry in the first row is. First row, second column, I'm left with a 2 by 2 submatrix. First column, -2, 2. Second column, -5, -1. That's the 2 by 2 submatrix whose determinant I must take right here. Then add the third number in the first row, 4, times the determinant of the 2 by 2 submatrix obtained by deleting the first row and third column. That submatrix that you see right there. -2, 2 for the first column, 4, 3 for the second column. Okay, it's very easy to make mistakes here, so you got to be careful. -1, determinant of this one's going to be 4 times -1 is -4, minus -5 times 3 is minus -15. Oh boy, so easy to make mistakes. Then minus -3 is +3 times the determinant of this will be -2 times -1 is +2, minus the product of these two things is minus -10. Then add 4 times the determinant of this one. -2 times 3 is -6, minus 2 times 4 is -8. Simplify. Being careful not to make a mistake. This is the same as negative 4 plus 15, which is 11, times negative 1 is negative 11. This thing is the same as 2 plus 10 is 12, so I get 3 times 12 is plus 36. And this thing is negative 14 right there. This is the same as plus 4 times negative 14, which is going to be the same as minus 56. And this becomes negative 11 minus 20 is negative 31, and I don't need to check the answer. I remember offhand from before that that is right. Negative 31 is the answer for the determinant, and that is the answer for part A. You could check this by doing cofactor expansions across some other row or some column. If you did it across the second row, for example, the main thing that's different is that the signs of the coefficients, though the coefficients themselves could be negative, don't go plus, minus, plus. They go minus, plus, minus. So that's something that you may or may not know. Again, you should also try it with row operations. If you've learned about how to do that, it would be good to check calculating the same determinant with row operations, but I'm not going to take the time to do that. Part B. What about the determinant implies that A is invertible? We've already said that. The determinant of A here is negative 31. It's non-zero. The fact that it's non-zero implies A is invertible. A inverse exists. Okay? The fact that it's non-zero, you could write that out in words. Anytime a square matrix has a non-zero determinant, that means that square matrix is invertible, which also is sometimes called non-singular, non-special. Okay, not a rare thing, a very common thing. When the matrix has a zero determinant, that's rare, that's special. We call it singular, and in that case, it would be non-invertible. So invertible goes with non-singular, non-invertible goes with singular. Okay, it's a bit strange. C, again, find the determinant of the inverse matrix without doing much work is the way I phrase it here, meaning without finding A inverse itself. It's based on a property of determinants that the determinant of a product is the product of the determinants. That's a true fact in general when you've got two square matrices, A and B, of the same size, the same dimensions. If you apply this to the product of A and A inverse, assuming A is invertible, you could write this, that's the determinant of A times the determinant of A inverse. But A times A inverse is the identity matrix, the n by n identity matrix, whose determinant is the product of the numbers on the main diagonal. And by the way, that's what helps you with the other method for finding the determinant. When the matrix is diagonal or even upper triangular, the determinant is the product of the numbers on the main diagonal. This is a 1. Therefore, these two things are equal. And therefore, the determinant of A inverse, solve for it, it's going to be 1 divided by the determinant of A. That's 1 divided by negative 31, or negative 1/31. Okay? So that's our shortcut formula in the case where A is invertible for finding the determinant of A inverse. It's 1 over the determinant of A. Okay? Which is pretty nice. On to page 3. Page 3 is a more abstract set of problems. And actually part A I did on my exam 1 review, but I think it's important enough to also do it here on the exam 2 review, though again, these things may be on your exam 1. It's an important enough thing. Okay? A is an m by n matrix, so that's m rows and n columns. You have to multiply A by an n-dimensional vector, a column vector we're talking about here as a matrix. That would be an n by 1 matrix, column vector. In words, with appropriate terminology, describe how to use the original definition of how to compute the product, A times x. Do not describe the shortcut, and by shortcut I mean the dot product trick, taking the dot product of the rows with the vector, the column vector. Do not describe the shortcut. Okay, so this is something I emphasize very, very strongly whenever I teach linear algebra or differential equations with linear algebra, what this means. And in words, you could say A times X is a linear combination of the columns of A with the entries of X, or components of X, as the weights. Okay, so there we are describing how to do A times X by definition. This is a good idea, is the basic idea of why we would want to of how we define A times X. It's done this way so that A times X also defines a linear transformation. T of X equals A times X will be a linear transformation. That's why we define it this way. Linear combination of the columns of A with the components of X as the weights, the numbers or coefficients in front of the columns of A. If you wanted to write this out in an equation, you could write A times X is, well, we could label the columns of A with, say, lowercase a's, vectors. These are column vectors. A is m by n, so there's m rows. Each of these columns is m-dimensional, and there are n of them. These AIs are in Rm. They're m-dimensional because there's m rows, and there are n column vectors because A has n columns. X would have n entries. You got to multiply by an n-dimensional vector. I already said that. N components. Label them x1 through xn. To be a linear combination of the columns of A with these components as the weights means form this linear combination. x1 times a1 plus x2 times a2, etc., plus in the end xn times an. And since all these a's are m-dimensional, this linear combination is also m-dimensional. This corresponds to a linear transformation that takes n-dimensional vectors and maps them to m-dimensional vectors. Okay, the order with the dimensions of A gets switched around. Part B. Let capital B be an n by p matrix, n rows and p columns. You can see the subscript goes up to p. These b's, the bi's, are in Rn, and there are p of them. Part 1, assuming what you've done in Part A is correct, write down the defining equation for A times B, the matrix capital A times the matrix capital B, and what are its dimensions. Okay? First of all, you should think about whether it can be done. Maybe we should answer the dimensions first. A times capital B is going to be, first of all, A is m by n, and B is n by p. Because the inner numbers match the n's, that's what allows us to do this multiplication. And the answer is going to have dimensions that are m by p. Take the outer numbers, m and p. That's the answer for part 2. But how do you define A times B? And I don't mean the shortcut. I don't mean with dot products of rows on the matrix on the left with columns of the matrix on the right. I don't mean that. I didn't say that here, but I don't mean to describe the shortcut. It's the defining equation. I could just write down the answer and tell you it's the answer based on memorization, but I think it's also useful to reason it out. First, let's think about B times an arbitrary vector y in Rp, a p-dimensional vector y. Based on what I said in part A up here, this equation here, I could write this as a linear combination. Scalar y1 times the vector b1 plus the scalar y2 times the vector b2, etc. The last term is going to be the scalar yp times the vector bp. What would happen if I multiplied both sides of this vector equation on the left by a times the vector by, well, it would be a linear combination of the columns of A with the vectors, with the components of this vector as the weights. But let's also think of it in terms of A times all this stuff, and use the fact that linear transformations are operation preserving. Effectively, it's like the distributive property holds. I can effectively multiply the A through each of these terms, add the results, and also factor out scalars. With a little bit of work, I could write this as y1 times ab1 plus y2 times ab2, etc., plus in the end yp times abp. And that is a linear combination of some vectors. By definition, that's this matrix, ab1, ab2, etc., for the columns up through abp times the original vector y. And that means that this expression is the answer for part A, or part 1. Write down the defining equation for AB. That's the defining equation for A times B. It's a matrix whose columns, p columns, are the matrix on the left with the columns of the matrix on the right. Okay? And it is going to be m by p. There's certainly p columns. Are all these vectors m-dimensional? Yeah, they are. Going back up here, it's like I'm multiplying a times x. I got m-dimensional vectors. Okay? So if you don't really know this stuff well, this seems pretty confusing. If you want to know linear algebra well, this is essential. Okay? You got to know this stuff. All right, 5 and 6 are some fill-in-the-blank problems related to spanning and linear independence. Now, actually, for my particular differential equations with linear algebra course, I delay talking about linear independence until after we started talking about vector spaces in the abstract. But even if you're in my class for that, differential equations with linear algebra, it's still worthwhile for you to learn a little bit about linear independence here before you get to the abstract vector spaces, and that's what we're going to do here. I do linear independence early when it's a pure linear algebra course. Let A be an m by n matrix. This system is consistent, meaning it has a solution for all constant vectors b in Rm if and only if the matrix A, the coefficient matrix, has a blank position in every blank. Okay, I'm assuming you've got some experience with this and indeed solving such systems by creating augmented matrices and doing row operations. If A, the coefficient matrix, not worried about the augmented matrix with the numbers on the right, if that has a pivot position where there's a leading 1 in the RREF, in every row, that's going to be enough to say it's got a solution. Why? You might wonder why. Well, if you think about row reducing A and maybe including a dashed line and having an augmented matrix here, I'm not going to draw it all out, but if you get a pivot position in every row, that's going to mean there's no way the system is going to be inconsistent, because the only way the system becomes inconsistent is if you have a row of zeros for the coefficient matrix part and a non-zero number to the right of the dashed line for the entire augmented matrix, because then you get a contradiction like 0 equals 1 or something. That's the only way you get inconsistency. If there's a pivot in every row, that won't happen. Okay? We're talking about the coefficient matrix here, A. That's not what this is. This is, I'm imagining this to be an augmented matrix where I put the numbers from the B vector on the right of the dashed line. This in turn is true if and only if the blank of A span blank. Okay, the columns of A span what? Rm. Okay, because why? For A of x to equal B, no matter what B is an arbitrary vector in Rm, that means the column space of A has to be m-dimensional, which means the columns of A, the set of all their linear combinations, has to be m-dimensional as well, all of Rm. This in turn is true if and only if each B in Rm is a blank of the columns of A. Linear combination. That's how you create the column space of A, is you consider the set of all linear combinations of the columns. It's going to be true. That's going to be true. It's going to equal all of Rm when the set of linear combinations will give you any arbitrary B in Rm. This in turn is true if and only if the image of the linear transformation T from Rn to Rm, notice again the numbers get switched around here. You multiply, you plug in n-dimensional vectors into T, you find the output by taking A times that vector, A times x, you'll get an m-dimensional vector because the columns of A are m-dimensional. Defined by that equation is onto is the key concept. It's an onto function. Finally, this is true if and only if T is, oh wait a minute, okay. I got these mixed around. True if and only if the image of the linear transformation is all of Rm. Yeah, the image. Which is true if and only if T is onto Rm. Okay? It's an onto function. This fill-in-the-blank stuff is about unique solutions, kernels and null spaces, linear independence. A is again n by n. Assume B is in Rm now. That is, well, yeah, same as before. A possible output of the corresponding linear transformation is a vector such that this equation has a solution. Depending on what m and n are, in general, it's possible it may not have, but I'm assuming it does have a solution. Then it's got a unique solution, if and only if A has a pivot position, but now it's in every row. Why? Every column. Why? Well, think about the opposite. If there was not a pivot in every column for the coefficient matrix, then when you go to RREF, one of the columns would not have a leading one. When you're thinking about the, whether you're thinking about a homogeneous system or a non-homogeneous system, there would be one of these that does not have a leading one. It's not necessarily in the last column. It could be in the second to last, for example. In general, that's going to correspond to a free variable, either for a homogeneous system or a non-homogeneous system. So for that to not happen, we need a pivot position, a leading one in every column for the coefficient matrix, not the augmented matrix. This in turn is true if and only if the columns of A are linearly independent. And again, for my differential equations and linear algebra class, we haven't talked about that yet. Linear independence essentially means the homogeneous equation has only the trivial solution. Ax equals 0 has only the trivial solution. That's what linear independence means. And that's actually described in the next sentence. This is true if and only if the homogeneous equation Ax equals 0 has only the trivial solution. This in turn is true if and only if the linear transformation defined by that equation has a solution set to this homogeneous equation which is only trivial, only the 0 vector. Or I'd accept trivial here as well. Finally, this in turn is true if and only if the linear transformation is 1-to-1. And we're also going to look at a proof later on in this practice exam showing that a linear transformation is 1-to-1 if and only if the kernel is trivial. That's going to be one of the problems, is that proof. Next problem. T is a linear transformation from R3 to R4. Its matrix, I'm calling B, would be 4 by 3, 4 rows, 3 columns. We multiply it by 3-dimensional vectors to get a 4-dimensional output. S is a linear transformation whose matrix, I'm calling A, is 3 by 4. We've got to multiply it by a 4-dimensional vector to get a 3-dimensional output. Part A, find a formula for the composite S compose T, where you apply T first to go from R3 to R4, and then apply S second to go from R4 back to R3. The composition goes from R3 to itself. It's ultimately defined, and you should know this without me telling you, by this equation, a times b times x. So to find a formula, we need to find a times b. Okay, so z equals s composed t of x is ultimately a times b times x. And now, for the purposes of doing this problem, we can use the shortcut formula involving dot products. We don't have to go back to the definition of a times b. So here is a, here are its columns, 4, 1, negative 2, negative 3, 0, 1. I'm looking here, 3, 4, 4, 1, negative 2, 0. And then for b, its first column is 1, 0, negative 2, 3. Its second column is 2, 4, 3, negative 3. Its third column is negative 3, 5, 1, 1. That's got to get multiplied times the vector x, which is three-dimensional, to come up with the formula. I could just write this as a boldface x. I'm just really going to multiply these matrices. This is 3 by 4. This is 4 by 3. The number of columns, 4, matches the number of rows, so I can do the multiplication, and the answer is going to be 3 by 3. I'll do it as quick as I can. For the first row, first column, it's the dot product of the first row with the first column, like that. So hopefully you don't make a mistake. 4 plus 0 minus 6 plus 3. So we ultimately get 4 minus 6 plus 3 is 4. Negative 2 plus 3 is 1. I better double check in the end here that I don't make a mistake. I do have the answer here somewhere. Yeah, okay, it's there. 1 is the first one. First row, second column is going to be the dot product of the first row here in the second column. 4 times 2 is 8. Minus 12 is negative 4. Plus 9 is positive 5. Minus 3 is 2. Yep, I do see it's matching down there. If you can't see it, if it's not showing up on, I'm not sure if it's showing up on the video. Here's the answer, by the way. And so let's now double check it. Continuing. Oops, just a second here. Hang on. I want to put that back down here so I can see it. First row, third column. 4 times negative 3 is negative 12. Minus 15 is negative 27. Plus 3 is negative 24. Plus 1 is negative 23. Yep, I'm looking at the answer. That's right. Second row, first column. Look at the second row here in the first column there. 1 plus 0 minus 8 is negative 7. Minus 6 is negative 13. That is correct. Second row, second column, 2, 0. Plus 12 is 14. Plus 6 is 20. This is a 20. Second row, third column, negative 3. Plus 0. Plus 4 is 1. Minus 2 is negative 1. And yeah, that's right. For the last row here, I'm looking at the last row here. Negative 2 times 1 is negative 2. Plus 0. Minus 8 is negative 10. Plus 0 is negative 10. Looking at the answer, that's right. Yep, that's a negative 10 there. Not a 70. Negative 10. And then negative 4 plus 4 is 0. Plus 12 is 12. Plus 0, it looks like this is a 12. And yes, that's right. Finally, this is a 6. Plus 5 is 11. Plus 4 is 15. Plus 0. The final answer is 15. I could consider this to be the formula. I could also multiply it out. Okay, that is part A. That'll be good enough. And this again is the vector x. All right, part B. Is S composed T 1 to 1? Use appropriate row operations with technology. I'm going to use my calculator to help you explain why or why not. And we'll use the ideas from the previous page. Is there a pivot in every column or not? We can just look at the coefficient matrix. We can just look at this one. We don't have to think about an augmented matrix. So let's get that into our calculator here. We'll also do row operations for part C to decide whether it's onto or not. And actually just doing one set of row operations will be enough by something called the Invertible Matrix Theorem. I'll talk about that in a second. Let's see, go to matrix mode. Oops, not that. matrix mode second there. I want to edit, say the first matrix, make it 3 by 3. We're talking about the coefficient matrix. I'm looking at this matrix right there. 1, 2, negative 23, negative 13, 20, negative 1, negative 10, 12, 15. And then go second, oops, escape there. Go back there and do math. RREF, I could also go up from the bottom, but it's right there. The matrix is matrix A. What typically happens with the 3 by 3 matrix is the RREF is the identity matrix. It may or may not be here. It is. There is, then this helps us answer both B and C. By what we talked about on the previous page, there is a pivot in every column. There's a leading one in every column of this coefficient matrix, which also means because it's a square matrix, there's got to be a pivot position in every row. So the answer to both of these questions, B and C, is yes. Yes for 1 to 1 is because there is a pivot position, or just pivot for short, in every column. So the corresponding homogeneous system would have no free variables. And C is also yes. You could say there is a pivot position in every row. So the system will end up being consistent in that case. You also could quote the invertible matrix theorem. With a square matrix like this, if there's a pivot position in every column, that's enough to say the matrix is invertible. And that's also equivalent to saying there's a pivot position in every row. And other equivalencies include the fact that with the square matrix, the linear transformation is going to be 1 to 1 if and only if it's onto. Those are various kinds of reasons that you could give, okay, for why the answer is yes. By the way, with these particular matrices, you actually could do another linear transformation that is T compose S of Y, say, and could be computed as B times A times Y. And it is possible to compute B times A. B is 4 by 3, A is 3 by 4. The 3's match, your answer would be a 4 by 4 matrix. And it turns out, you should check this, that matrix is actually not invertible, and that means T compose S is not 1 to 1 and T compose S is not onto. Which makes intuitive sense if you think about the dimensions for this. T compose S goes from R4 to R3, R4 to R3, and T goes from R3 back to R4. Because of this, S compresses the dimension from a higher dimensional space to a lower dimensional space. S can't possibly be 1 to 1. And that is enough to say the composition can't be 1 to 1 as well. I'd encourage you to think about that. And that also means the composition is not onto. T compose S in that case. Okay? But with this other way, it did work. It was 1 to 1 and onto. And I encourage you to think about that intuitively as well, that can happen. It didn't have to be, but it was in this case. Number 8, solve a difference equation initial value problem. I am teaching right now the combo course, differential equations with linear algebra, and so we're talking about both differential equations and difference equations. But even when I teach a pure linear algebra class, I often talk about difference equations. Oh, and there's a typo here. There should be an xn minus 1 there as well. And to solve it, I'm just telling my students the answer. I'm telling you the answer. It turns out, well, you can figure it out by iteration. Maybe I should do that. Xn is going to be a times xn minus 1. But xn minus 1 is a times xn minus 2. And that equals a squared times xn minus 2. And xn minus 2 is a times x minus n minus 3, etc. And the pattern says that in the end, you get a to the nth power times x sub n minus n, which is x sub 0. That's an abstract formula for the answer, but I want to solve it. I want to actually simplify this. So I need to raise the matrix 2, 0, 0, 3 to the nth power and multiply times the vector 1, 2. Now in general, that's a hard thing to simplify when your matrix is not diagonal, but this matrix is diagonal. The numbers off the main diagonal are all zeros. And because the matrix is diagonal, A is diagonal, I can do this matrix power just by raising the numbers on the main diagonal to that same power. And I guess you could say the zeros are also raised to that same power, but that would still give you 0, so you don't need to write it. Since A is diagonal. When it's not diagonal, it gets complicated. That gets into content for exams 3 or 4 that we end up doing related to something called diagonalization. It's not a topic yet. Simplify this by multiplying it out. 2 to the n times 1 is just 2 to the n, and 3 to the n times 2 is just 2 times 3 to the n. So there's your solution. There's a direct formula for the vector xn. Okay? That's what we mean to solve that difference equation. And you can plot these points in the plane as n varies, and that can be interesting. It'll make the origin what's called a source, because these things that are raised to the nth power are bigger than 1. It's also called a discrete dynamical system, what we're doing there. I'm getting close here, a couple more pages. When I've given this problem in the past, students typically find it difficult because it's a little weird. Show work to find a formula for a linear transformation from R3 to R, one-dimensional space, the real line, whose kernel, which will be non-trivial, as it would have to be when you're going from a higher dimensional space to a lower dimensional space, and it's going to contain these 3 points. Now, in general, those 3 points don't have to be in a plane that would necessarily go through the origin, 3 arbitrary points. However, for extra emphasis, I'm saying you can rest assured that the kernel of T contains the origin. I'm saying that the plane containing these 3 points does go through the origin, and you're just trusting me on that. You might want to see if you can figure out why. Because of this fact, you could also think of the kernel of T as being parallel to the 3 position vectors of these 3 points. What are position vectors? Probably better to call them displacement vectors. I mean, you could call them, or change in position. That's a better phrase there. I should have called it change in position. Change in position vectors, displacement vectors between the points, are arrows that go from one of those points to the other. And you can find them, if you know about vector arithmetic, with vector subtraction. Let me give these points names. I'll call them P, Q, and R. P, Q, and R. That's not Euclidean space. Sounds weird, sounds difficult. Hint, a cross product may be helpful, and there are infinitely many correct answers, but also infinitely many incorrect answers. Make sure your one is the infinitely many correct ones. What in the world here? I'm saying these points go through the origin. I want the plane that contains them to be the kernel of the linear transformation. Planes to the origin have an equation, something times x plus something times y plus something times z equals 0. Emphasis on the 0. The part on the left could be thought of as a linear transformation, taking a 3-dimensional point, x, y, z, and mapping it to a number in R. So the answer is essentially going to be the left-hand side of the equation, equaling 0. That left-hand side, whatever it is going to be the formula for the linear transformation. Taking a 3-dimensional point, mapping it to a number. So we just need to find the equation of the plane. And the way to do that is to take those displacement vectors, change in position, and find their cross product to get a normal vector for the plane. Those would be the coefficients of x, y, and z in the equation. So one vector that lies in the plane is going to be, say, v equals, I'll write it as p minus q, where I'm thinking of p and q as being, well, initially here as points, but I could imagine these being row vectors as well. I'll write V. Okay, I could write it as a row vector. It's fine. Let's just do it as a row vector. P minus Q. Subtract coordinates. -6 minus -13 is +7. 1 minus -2 is +3. 2 minus 1 is 1. So the vector 7, 3, 1, I'm writing it as a row vector here. I could write it as a column vector, is a vector parallel to this plane. Another one called W, say P minus R, is also going to be in the plane. Look at these points. -6 minus 7 is -13. 1 minus 3 is -2, and 2 minus 1 is 1. So hopefully I have not made a mistake here. Just double checking things. Yeah, this looks good. Okay, that's a -13 there, not a -b. That's a -13. A normal vector for the plane is, for example, v cross w, or any scalar multiple of that cross product, including w cross v. And to find the dot product, well, there's various things you can do, but what I always end up doing is taking a determinant of a 3x3 matrix. The lines here mean take the determinant. It's alternative notation for the determinant. V is 7, 3, 1. W is -13, -2, 1. Take the determinant of this. In spite of the fact that I hat, j hat, and k hat, the standard unit vectors, are not numbers, they are vectors. Just pretend they're numbers for the sake of doing this formal determinant. It's not a true determinant in the usual sense. So do it across the first row there. I hat, the first entry, which is, by the way, 1, 0, 0, times the determinant of the 2x2 submatrix I get by deleting the first row and first column. I'll write it with this absolute value notation, though determinants can be negative, so that's a little deceiving. It's not really absolute value notation. Minus, don't forget to go plus, minus, plus here across the first row, j hat times the determinant of the 2x2 submatrix that I get when I delete first row and second column. 7, 1, -13, 1, plus k hat times the determinant of this 2x2 submatrix. 7, 3, -13, -2. So I get I hat times 3 minus -2 is 5, minus j hat times 7 minus -13. That is a plus 20, but then we have a minus sign there. And then plus k hat times 7 times -2 is -14, minus -39. That simplifies to 39 minus 14 is 25. So it looks like n, our normal vector, could be thought of as 5i hat minus 20j hat plus 25k hat using I hat, j hat, and k hat notation. As a column vector, I could write it as 5, -20, 25. And that means t of x, y, z is going to be 5x minus 20y plus 25z. That's one answer. Another answer is any non-zero scalar multiple of that. How about divide everything by 5? X minus 4y plus 5z. These are two of the infinitely many linear transformations from R3 to R whose kernel contains these 3 points. It's a plane through the origin in R3 containing those 3 points. Okay? One of infinitely many correct answers, but there are also infinitely many incorrect answers. Just double checking my answer. Yes, it looks good. Hang on here. This is a proof. There's one more page. The last page goes fairly fast. Okay? Not much work to do on the last page. Suppose T from Rn to Rm is a linear transformation. Prove that T is 1-to-1, also called injective, if and only if the kernel of T is trivial. I mentioned this a little while ago with a different problem. Proof. This is an if and only if proof, so it's got two directions to prove. One direction is essentially the definition of one-to-one, and the other one's a little trickier. Which one is the easier direction? I think it's this direction that's easier. If t is one-to-one, the kernel is trivial. Yeah, that's the easier direction. Suppose t is one-to-one. That means distinct inputs get mapped to distinct outputs. We also know that any linear transformation maps the zero vector to the zero vector, although these zero vectors are in different spaces. This zero vector is in Rn, the domain. This zero vector is in R, is an element of Rm. This funny looking thing means is an element of Rm, the codomain. Okay? But that's true, and that's something we're using here. My students, you may use it. It's certainly easy to prove, although it's a little tricky. It's related to the fact that linear transformations are operation preserving. So, for example, this is just a side calculation. T of 0 can be written as t of 0 plus 0, which, since t is operation preserving, is t of 0 plus t of 0. And then you can effectively cancel a t of 0 on both sides to say that 0 equals t of 0. That's the cancellation property that holds with vector spaces in general. We're talking about Rn and Rm here, not general vector spaces yet, though. That will come up a little bit in the last page, a little introduction to vector spaces. Since t of 0 is 0 and t is 1-to-1, no other non-zero vector could get mapped to the zero vector. No other vector, and I'm implicitly meaning other non-zero vector, can get mapped to 0. The zero vector in Rm, the codomain, i.e. t of x equals 0 has only the trivial solution. X equals 0. But that exactly means that the kernel is trivial, because the kernel of t is by definition the solution set of this homogeneous equation. But this means, by definition, that ker of t, the kernel of t, is just the zero vector. Okay, so that part's easier. The other part's a bit trickier. Suppose the kernel of t is just the zero vector. I need to show that t is 1-to-1. The operation preserving property will come into play here. If t were a nonlinear transformation, well, you wouldn't necessarily talk about kernels in such a situation, but just because a nonlinear transformation only maps the zero vector to the zero vector, for example, does not mean that the nonlinear transformation would be 1-to-1. We need the fact that t is linear, so it's operation preserving. So how do we do this? How do we show it's 1-to-1? Start by supposing t of, say, x equals t of, say, y. If we could show that x equals y, we'd be done. Because 1-to-1 means distinct inputs get mapped to distinct outputs. Another way of saying that is if the outputs are the same, the inputs must have been the same. So we want to show x equals y here. It's not clear how to go. You might wonder, can I cancel the t's? The answer is no. Can I apply t inverse? The answer is no. T inverse may not even exist, and an m may not be the same. I cannot do that. So what do we do? Well, it's a little trick. This means subtract t of y from both sides. T of x minus t of y equals the zero vector. But since t is operation preserving, OP for operation preserving, t of x minus y must be the zero vector. in general operation preserving, OP means T of alpha x plus beta y, where alpha and beta are constants, scalars, is alpha of T of x plus beta of T of y. I'm using that here to say these are equal when alpha is positive 1 and beta is negative 1. But we're basically done. This means x minus y is in the kernel. It's an element of the kernel T, which is just the 0 vector. Therefore, x minus y equals 0, so x equals y. And that proves that T is 1-to-1, QED. Praise the Lord, we're done. Okay? But it's tricky. Okay, so this is a trick you should think about in practice. Comes up in other contexts as well. All right, last page has got 4 problems, but they all go pretty fast. T from R3 to R3 is a linear transformation that reflects each vector or point, you might say, through the plane z equals 0. It's got this formula. Find the standard matrix of T. Got to know something here. Before I write down the standard matrix, let's just think about this visually. If you draw a 3-dimensional coordinate system with, say, a positive x-axis this direction, a positive y-axis this direction, and a positive z-axis upward, reflecting across z equals 0 means reflecting across the xy plane. So you've got a point up here above the xy plane, or a vector from the origin to that point. It's going to get reflected to the opposite point below the xy plane, same distance from the xy plane. Okay, that's what the mapping is doing geometrically, and it does just negate the third coordinate is the point of this formula. As far as its standard matrix goes, you just need to remember that the first column of the standard matrix is going to be T of, you could call it I hat for the standard unit vector in the x direction, j hat for the standard unit vector in the y direction, and k hat for the standard unit vector in the z direction. Or some books call these E1, E2, and E3. And in general, when you've got more than 3 dimensions, that's a good thing to do. Typically, we're thinking of these things as column vectors. E1 would be 1, 0, 0. That's the same as I hat. J hat equals E2 is 0, 1, 0. And K hat equals E3 equals 0, 0, 1. And this is how to find the standard matrix of T. In my lectures for diffeq with linear algebra, I describe why. We're just trying to get an answer here. Use this formula. Plug in 1, 0, 0, you get 1, 0, 0. Thinking about column vectors in the matrix, thinking about row vectors here, be able to go back and forth. Plug in 0, 1, 0, E2, I get 0, 1, 0. Plug in 0, 0, 1, I get 0, 0, negative 1. There's the answer. That's the standard matrix for this linear transformation. If there's a standard matrix, does that mean there's a non-standard matrix? And the answer is yes. Matrices for linear transformations are always relative to a basis, and basis comes up on exam 3. 12, let A be a 3×3 matrix with the property that the linear transformation is onto. By thinking about the pivots of A, explain why T must also be 1-to-1. We talked about this earlier with pivots in every row and every column. Yeah. A little explanation here. T being onto implies that its matrix A has a pivot position, if you will, in what? Every column or every row? It was every row. So you get a consistent system no matter what the right-hand side is. And since A is 3×3, a square matrix, these two things imply A also has a pivot in every column. We're talking about the coefficient matrix here, A, not an augmented matrix with the right-hand side numbers to the right of dashed line. This has a pivot in every column. And that means when you solve the corresponding homogeneous system, there are going to be no free variables. The kernel is trivial. I'll go ahead and just say that. That means the kernel of t is trivial, just the zero vector. And that means t is 1 to 1. Okay? 13 and 14 are get more abstract. Vector spaces and more general linear transformations. In 13, a linear operator. I probably should have added the word differential operator here to emphasize it involves a derivative. T has this formula where y is a function of t. I also could have used f for my general function of t. What does this mean? What do you plug into t? You plug differentiable functions into t. Or to be a little extra careful, it's nice to plug in continuously differentiable functions. You could think of, for example, t as being a mapping from the vector space of all continuously differentiable functions defined in the entire real line. That's a standard symbol for that kind of thing. This symbol means the collection set of all real valued functions that are defined and differentiable with continuous derivative on the entire real line. That's a mouthful, huh? That's a vector space. You can add any two such functions and get another such function. You can multiply any such function by a scalar and get such another function. And you can verify associative property, commutative property, etc. for both function addition and multiplication by scalars all works if you know about vector spaces. What is it mapping to? Well, since I'm differentiating and since the derivative is assumed to be continuous, it's mapping to just CR, where I do not put a superscript above the C. This represents the vector space of all continuous real valued functions, defining continuous over the entire real line. T is this kind of mapping. Take a function, find its derivative, and add 3 times the function. The goal is to find the output of this function when the input is cosine of 4t, a function of little t. So what do you need to do? It's easier than it might seem. You just need to plug it in place of y. You need to differentiate it with respect to t. The prime means with respect to the t variable. And you also need to add 3 times the function, 3 times cosine of 4t, and just simplify. The derivative is, by the chain rule, negative 4 sine 4t. And then this simplifies to itself, essentially, plus 3 cos 4t. And that is the answer. That is the image or output of this function cos 4t when you plug it into capital T. This linear differential operator, which is a linear transformation between, for example, these vector spaces. By the way, I could use other vector spaces for the domain and codomain. I could use C2 of R there and C1 of R there. Twice continuously differentiable to once continuously differentiable, twice meaning the second derivative exists and is continuous. There's infinitely many choices I could have here. 14 is the last question. Does the set of all functions of this form, where a and b are arbitrary real numbers, form a vector space? Explain why or why not. The set of all such functions, the collection of all such functions, is certainly a subset of, for example, C of R, for example, or C1 of R, or C2 of R, or C3 of R, or C infinity of R. These functions are, in fact, infinitely continuously differentiable. They have derivatives of all orders, which are all continuous functions. But it's fine to just remark this, and this is a vector space. Does that mean we're done? Does that mean this is a vector space? No, we need to show it's more than just a subset. We need to verify the vector space properties. There's something called the Subspace Test, though, that allows you to just verify 3 properties. First, and by the way, the answer is going to be yes here, although you may not know that ahead of time, although in my lectures I do say that. Is the 0 vector in this set? The answer is yes. But wait a minute. I don't see a 0 vector in the usual sense. Well, it's the 0 function. That's the 0 function. The elements of this vector space are functions. The 0 function can be written in this form. Take a and b to be 0. Let's give the set a name. Let's call it W. This is in the right form to be in W. So the 0 vector in the form of the 0 function in this vector space is in W. That's the first thing to check. Second thing to check is that it's closed under vector addition, or in this case, function addition. If I have two such functions, a1 e to the negative 3t plus b1 e to the 4t, and a2 e to the negative 3t plus b2 e to the 4t, is the sum also in W? And the answer is yes, because of properties of number addition, like the commutative property and the associative property. I can rewrite this as the number a1 plus a2 e to the negative 3t plus the number b1 plus b2 times e to the 4t, and that is in the right form. A scalar times e to the negative 3t plus another scalar times e to the 4t. This is an element of W. So this means W is closed under addition. And finally, last thing to do, multiply an arbitrary function in here by a scalar, say call it alpha. Is the result still in this set? And the answer is pretty clearly yes, because I can distribute the alpha through here and write it as alpha a e to the negative 3t plus alpha b e to the positive 4t, and that is in the right form as well. A constant times e to the negative 3t plus a constant times e to the 4t, that's in W as well. And so by the subspace test, that implies, all these three things imply that the answer is indeed yes. This is a vector space because it's a subspace of a known vector space. All subspaces are vector spaces. All vector spaces are actually subspaces, at least of themselves. We'll get more into heavy-duty theory for exam 3 and a lot more about linear independence and bases and changes of coordinates. Thanks for watching.